So in this little lecture we're going to talk about the Doppler effect, and that is the effect that moving sources or moving observers have on the perceived sound. And in some cases this perceived sound is actually a real sound. When we use the word perceived, it makes it sound like it's sort of fictitious. But in some cases the Doppler effect, the result of motion of the source, for example, physically changes the wave. And so the Doppler effect is a real thing. It's not an imaginary effect. If the observers are moving, then in the sense it's more of a perceived change in the frequency. So most people have heard fire engines and things like that go by, and they've heard the pitch change as the fire engine passes by from a higher pitch to a lower pitch. This shouldn't be confused with the sound volume, the loudness getting higher or lower. That's a different thing. When the source, like the fire engine, is coming closer to us, yeah, it gets louder as it gets closer, of course. And sometimes our ears can sometimes perceive that as a change in pitch. But if a source is moving toward you at a constant velocity, there's a change in pitch of that sound relative to what the source sends out. But that change of pitch does not change as the source gets closer. So this isn't something that's a function of distance. It's just a function of the velocity of the source and the observer. So if we look at a little animation here of circular waves being emitted by the source and then two observers sitting here, we have one observer here, the blue dot, one observer here, the red dot, and the source in the middle is the green dot. If we just play this, we can see the source giving off circular waves, circular sound waves, and these are the wavefronts. So we think about kind of like ripples on a pond. If you put your finger on the surface of water and wiggle it up and down, you'll get these little ripples created, and they propagate outward in a circular fashion. Sound is sort of like this. It sends out these wavefronts in all directions from the source, except sound isn't a transverse wave like water waves, surface water waves are. Rather, it's a longitudinal wave. But either way, we can draw these wavefronts. And these wavefronts again represent places where the medium has been displaced in a maximum direction, in a maximum sense, in the positive direction, the outward direction. So everywhere along this circle, the air has been pushed a little bit outward from its equilibrium position. Everywhere in between these circles would be a minimum. That would be places where the air has been pushed inward at a maximum displacement. So these are circular waves. So we're looking at if we kind of looked along this direction here, we would see a kind of a sinusoidal wave where the air is getting pushed out and then back in and then back out and then back in and back out and so on as the wave passes by. So again, sound waves are longitudinal, but either way, the same effect can be seen in transverse waves like water waves on a pond. So if we play this again, we see that these sound waves hitting the sources look exactly the same. The source here is sort of feeling or seeing or hearing whatever the same waves, same wavefronts as this source over here. There's really no difference. If I give the source some speed, if right now the speed of the source is 0, I can open this little box up and show that the speed here is 0. If I change the speed, and this would be in fractions of the speed of sound, I can change the source's speed, and it's going to travel to the right. And so when we do that, so it took a little jump. Let me actually, well, that's okay. So it's traveling to the right, traveling toward this blue observer. And you can see that the wavelength's a little bit shorter here. The wavelength that this blue observer is measuring is a little shorter than the wavelength over here that this red observer is measuring. So let me pause this, go back to time equals 0, and start over again. Let me first give the source a high speed, and then I'll start the time. Or I'll play. And you can see, if I have a high enough speed, you can see the wavefronts significantly compressed in the direction of this observer and significantly stretched out in the direction of this observer. So there goes the source moving to the right. As at every cycle, at every period of the sound wave, it gives off a ripple, a wavefront, a circular wavefront. And I'll pause that. And so you can see that the wavelength that this blue observer is going to measure is certainly shorter than the wavelength that the red observer is going to measure. So for a source moving toward you, you're going to measure a shorter wavelength. For a source moving away from you, like this person, you're going to measure a longer wavelength. And so how do we calculate frequency? Well, frequency is just the speed of sound divided by the wavelength. And the speed of sound for both observers is the same. We're assuming that there's air, of course. You have to have air for sound waves to travel. And the air is at rest. We're assuming there's no wind. And so these two observers are at rest relative to the air, but the source is moving through the air. So once these wavefronts are created, they just travel through the air at the speed of sound. And this observer measures that speed, and this observer measures that same speed. So they measure the same speed of sound, but different wavelengths. So we can continue to play that, and you can see that as the source moves past this observer is measuring a short wavelength on higher frequency. And now, and once the source has left, has passed by, this observer now is measuring a longer wavelength, lower frequency. So that's why there's a pitch change when the source moves past you. There's not a pitch change while the source is heading toward you. There's a difference in the pitch that you hear versus what the source emits, but that difference doesn't change as the source gets closer. What changes is when the source passes you, then it goes from a higher frequency to a lower frequency. So let's look at the mathematics behind this and think about how we would actually calculate an equation, derive an equation for the frequency that the observers measure. So if we look at this little figure here, we have a source moving to the right, and it's giving off these wavefronts like we saw in the last animation. This picture is showing a time period over 3 periods of the wave. So initially the source is right here. It gives off this red wavefront, but that red wavefront, it takes a while to expand to the size that it's shown right here. So in the process of this red wavefront expanding, the source moves to this point, point 1, and that's one cycle later it gives off the green wavefront. Another cycle later it gives off the blue wavefront, and then it gets to point 3 another cycle later, and it's just about to give off another wavefront, an orange wavefront. So the total amount of time here is 1, 2, 3 cycles worth of time, or 3 periods. Capital T is the period. And in this amount of time, the red wavefront, which was created at this point, has expanded to be this long, 3 wavelengths as measured by the source. So lambda 0 is the wavelength that the source measures. If the source were sitting still, lambda 0 is the wavelength that source measures. The source then, once the source moves to this point 1 here, this green wavefront was given off, but in the next 2 cycles that the source takes in terms of time to get to point 3, that wavefront has expanded 2 times the wavelength as measured by the source. When the source finally gets to point 2, it gives off that blue wavefront. It moves one more cycle worth of time to point 3, and in that time the blue wavefront moves or expands 1 wavelength worth of distance. So again, these wavelengths, these individual little circles, are little ripples in sound in a sense that travel outward away from the point where they were created. Once they're created, they just travel outward in all directions, independent of what the source is doing. It makes no difference. And so they travel at a certain speed, and so in a certain time they travel a certain distance, and that distance is equal to the wavelength that somebody would measure just standing there watching these wavefronts travel outward. So both Nancy and Pablo, they would agree that these wavefronts, if they looked at the actual wavefronts, one single wavefront for example, they would agree that this wavefront is 3 wavelengths long, with the wavelength as measured by the source. This one's 2 wavelengths long, this one's 1 wavelength long. But what they're really going to measure, what they're really interested in measuring, is the distance, not the length, not the size or the radius of one of these wavefronts, but rather what they're interested in measuring is the distance between wavefronts. So they want to know, what is this distance here? For Nancy, that's a smaller distance than this distance here for Pablo. So Nancy's going to measure a smaller wavelength, we'll call it lambda plus. Pablo is going to measure a longer wavelength, we'll call it lambda minus. So let's come up with an equation that relates these wavelengths. If we think about the geometry here, first think about Pablo. This distance right here from the red wavefront to the green to the blue and then to point 3, that's how many wavelengths is that? That's 3 lambda minuses going from the red to the green to the blue to the orange. That's 3 lambda minuses worth of wavelength. So what can we come up with an equation that relates that to some other things? Well, 3 lambda minus right here is this big distance right there. Well, the source started off at this point 0, and in this amount of time that this red wavefront expanded to get to this point right here, the source moved this distance right there. So we can write this full distance of 3 lambda minus all the way across here as being equal to the distance that the red wavefront has expanded, the radius of the red wavefront, plus the distance that the source has moved. And so that's what this equation is here. This is the radius of the red wavefront, 3 lambda 0, and then plus this is the distance that the source has moved. 3 times big T is the time that has gone by. Big T is the period, the amount of time between emissions of wavefronts. That's the period. And Vs is the speed of the source. Not the speed of sound, but the speed of the source. So velocity times time, 3t, gives us the distance the source moved. Add to that the radius of the red wavefront. That gives us this full distance of 3 lambda minus. So here's an equation we can use to relate these various wavelengths, these various distances, with lambda minus in here that we can ultimately relate to the frequency f minus that Pablo would detect. And at the same time, looking at Nancy measures what we call lambda plus. And so we're looking from the red to the green, from the green to the blue, from the blue to the orange. That's 3 lambda pluses. Well, what is that? What is that distance in terms of these other distances? Well, 3 lambda plus this distance that the source moved, I would get the full radius of the red wavefront. Or I could say that 3 lambda plus equals the radius of the red wavefront minus this distance that the source has moved. And that's what this equation shows right here. 3 lambda plus equals the radius of the red wavefront minus the distance that the source has moved. So just simply relating these distances through a little bit of geometry and thinking about how far the source has moved in the time, 3 big T's, we get those two equations of wavelengths. And then we go through and we manipulate some things, and we say, we cancel out these 3's, of course, and we substitute in for all these lambdas. For lambda plus, for example, we substitute in the speed of sound divided by f plus. For lambda minus, we substitute in the speed of sound divided by f minus. For lambda 0, we substitute in the speed of sound divided by f0. So f0 is the frequency that the source is emitting, f minus is the frequency that Pablo hears, and f plus is the frequency that Nancy hears. And then finally, the period of the waves can also be written as 1 over the frequency as emitted by the source. So making those substitutions, these two equations here and here turn into these two equations here and here. So we get these frequencies in the denominators now, and now we just combine some terms over here and change things around. Solve for f minus in this equation, solve for f plus in this equation, and that's what we get down here. So the frequency that Pablo measures, f minus, is equal to the frequency that the source is emitting, f0, times 1 divided by 1 plus v source, speed of the source, divided by the speed of sound. Or you could write it another way, keeping the speed of sound in the numerator there, speed of sound divided by speed of sound plus speed of the source. Either way. So this f minus is going to be a smaller number than f0. Pablo is going to measure a lower frequency than the source is emitting because of this factor in the denominator here. This thing in the denominator is bigger than 1, so the fraction is going to be smaller than 1. The whole fraction is going to be smaller than 1. Multiplied by f0 is something less than f0. On the other hand, Nancy is going to measure a higher frequency. Taking this equation here and solving for f plus, looks exactly the same as the equation for f minus, except I have a minus sign in here. So I've got f0 times speed of sound divided by speed of sound minus speed of the source, or f0 times 1 over 1 minus speed of the source divided by the speed of sound. Either one of those equations is fine. So this denominator then is a number less than 1. I've got 1 minus something. And as long as the speed of the source is less than the speed of sound, then these equations work. You get something greater than the speed of sound, then you have to analyze it physically a little bit differently than what we've done, because the source gets in front of all the wavefronts. So these equations can be used to calculate the frequency due to a moving source. Finally, if we think about moving observers, it's very simple. It's simpler, I guess, but maybe not very simple. So here we've got a source sending out these wavefronts. If I imagine Nancy heading toward the source, these wavefront distances haven't changed. So the wavelengths are going to be the same now. But now Nancy's moving this way. Relative to the air, she's moving this way. and she's going to be kind of encountering or hitting these wavefronts faster, more rapidly than if she were sitting still. According to her, these wavefronts have sped up. So it's really the speed of these wavefronts that is higher than they were before. The wavelength is the same. So looking down here, all we have to do is say, according to Nancy, the speed of the wavefronts is the speed that they have relative to the air plus her speed relative to the air. That's the speed of the wavefronts relative to her. And then, according to Pablo, the speed of the wavefronts are actually less. Or not. If we have Pablo moving away, he's kind of running away from the wavefronts. They're catching up with him, but they're passing him by, but not as fast as if you were sitting still. The speed of the wavefronts relative to Pablo is the speed of sound minus his speed. He's running away from them. VO is the observer's speed relative to the air. So if we think about Anna, we're running toward the source. She measures a higher speed of those wavefronts. Divide that by the wavelength that she measures, which everybody agrees on. She gets her frequency. So plugging in V plus equals V plus V0, dividing by lambda 0, we get this. And then simplifying some things through here, substituted in for frequencies, we find that the frequency that Anna measures, or Nancy, not Anna, Nancy, she measures a frequency of the source multiplied by 1 plus something here. And this is a bigger thing. This number is bigger than 1. This is 1 plus V observer divided by the speed of sound. That's a number bigger than 1. So Nancy running toward the source measures a higher frequency. But again, it's not because the wavelength has changed. It's because the speed of those sound waves, the wavefronts, has changed, according to Nancy at least. With Pablo running away from the source, he measures a shorter wave, or he measures a lower speed for those wavefronts. And so his frequency would be the speed of the wavefronts divided by the wavelength of those wavefronts. And so plugging in that the speed of the wavefronts relative to him is the speed of sound minus his speed. Divide that by wavelength. That gives us frequency. So simplifying through here ultimately gives us that Pablo running away measures a frequency equal to the frequency of the source multiplied by 1 minus some number. This number here isn't going to be a negative number. It'll be some number, but it's going to be less than 1. So he measures a lower frequency than the source measures. So in all these cases, there's changes in frequency, whether the source is moving or the observers are moving. But the physical differences are important to realize. If the source is moving, the wavefronts actually get compressed or expanded. So here we can make the source move. The wavefronts actually get compressed in this direction, expanded in this direction. And that's a physical change of the wavefronts. If the observers are moving, if all we're doing is having the observers move, then we have more of an apparent effect where somebody's just running toward the wavefronts and they appear to be moving faster than they really are relative to the air. But in either case, they still measure a different frequency. So whether the observer is moving or the source is moving, we get changes in frequency, but we do have different equations to describe those changes in frequency because there are different physical effects happening depending on who's doing the moving.